Uh, I would like to continue there where Molly stopped, but I intend to go a little bit more to the details, to the technical details in that case, especially to the power and communication system. So as Molly already said, so this is basically the prerequisite for all the other stuff which we intend to do, so especially for these train functions. Of course, then we need to have power as well as a communication possibility within freight wagons. Today, freight wagons are more or less dumb vehicles. Yeah, though there's no power in, there's no communication facility in, and pure mechanics, and this is intended to be changed. So, okay, to my person, so I'm with Alstom in Germany, have more than 30 years experience in TCMS system with a special focus on onboard communication systems. And I'm also a member of several working groups, especially working groups which are dealing with onboard communication systems. Originally, it was planned to have this presentation together with Florian Einzel from Deutsche Bahn, but unfortunately, so he could not make it, so I will present also his part. So, what's the scope behind the power and communication system? First of all, it's clear we needed to support power to the freight wagons. So this is the basic intention. And when it comes to the communication system, then we need to have, of course, a possibility to communicate. And here it was clear right from the beginning that if possible, we should adapt existing standards for using this. And this immediately led us to the TCN standard series. It's, that's the IC 61375 standard series about TCN. There was one constraint which we have coming from more or less from the mechanical design, and this was related to the coupler head itself, so the electrical part of the coupler. There, one requirement was to limit the number of contacts to the absolute minimum, and this didn't fit with that what we presently have defined in the TCN standards. So in the TCN standards, we are using standard Ethernet, requiring 4 coupler pins, or even, so in the next generation we will have gigabit Ethernet asking even for 8 contact pins. This is definitely not doable with the freight train, so there was already from the beginning the requirement to restrict this to 2 pins, and so the only technology which we can apply in that case, if we speak about Ethernet-based technologies, is a single pair Ethernet. So the after some analysis which has been done in the EDDP European project, where different candidates have been investigated and analyzed, the conclusion was as a primary choice to base on 10 base T1L, so the single pair Ethernet. As a fallback solution or alternative solution, we are still investigating this Powerline Plus, which is based on the IEEE 9001 standard, which is in that case using the Powerline for communication. Single pair Ethernet requires its own wires for communication. With the Powerline Plus, it would be possible to use the existing Powerline, which we have anyway in the system. For the upper communication layer, so as I already said, so the intention was to use that what is already existing in the TCN standard series, but this needs to be adapted a little bit, because we have some specialities with the freight trains which we didn't encounter in the passenger trains, so some changes will be necessary for supporting this. This all then should be used, as Molly already mentioned, for the support of different train functions. So I have here listed 5 train functions which are immediately connected to the communication system or affected by the communication system. There are, of course, a lot more train functions, which as well will use a communication system, but in that case on a pure application level. So train functions which have a more impact on the communication system. This is first of all the train composition detection. Then we have a passive consist detection. Passive consist here means this is a consist or a vehicle, a freight vehicle, which is powerless or defective, and for this reason cannot participate in the communication. So this has been called a passive consist here. Then we need to have a train wake-up function, to be able, for instance, in the yard to wake up a train for doing some tests or some operations. Also very important will be the train integrity function. So this is, of course, a safety-related functionality which we have to consider. And also a special function will be the automatic uncoupling, which is especially needed during yard operations. So when vehicles shall be decoupled and later on coupled to another train. And finally, also belonging to the communication system is the train-to-ground or train-to-cloud communication itself. So here we see a typical scenario of a freight train configuration. You see there are some differences compared to passenger trains. So we could have much larger number of freight vehicles. So presently it's specified for a train with up to 100 wagons and 4 locomotives. Up to 50 wagons can be powered by 1 locomotive. It means if we have a train with 100 vehicles, then we need to have an additional loco which is powering the second part of the train, or at least 1 additional loco. So the power which can be provided by 1 locomotive is about 3 kilowatts. And this means, so if we really have the maximum number of freight wagons in the train, then in medium, so each freight wagon can consume up to 50 watts, which is not really much, but should be sufficient for the essential functions. And yes, so power supply and power distribution along the train via the electric couplers, the same is valid for the communication system. A few words about the choice of the power supply system. So there was some process in that. Because in the beginning of the discussion there was a choice between different power systems. We see it on the left side here. So we have ranging from DC voltage 110 volt to using USC train line up to 3 kilovolts. There we defined some criteria which need to be fulfilled for freight trains. And the result was what we see on the right side, a short list of technologies. This was AC 230 volt, DC 400 volt and AC 400 volt in 3-phase. Oops, this was one too much. So based on this short list, there was further analysis conducted, especially looking at the number of contacts which are required in the electrical couplers. You see it here, a number of contacts. And so, judging about the pros and cons of each solution. And the final conclusion was what we see on the right side, to select a 400 volt 2-phase system, which is isolated, and only requires 2 contacts within the coupler. So of course, due to the symmetry in the wagons, we need to have 2 times 2 contacts in the coupler. The same is valid also for the communication system. So this was a conclusion for the power system. Now some words about the communication system. So I already said, the choice was to base on single pair Ethernet in that case. We need to have a redundant communication line for reliability reasons. And we have to support here up to 100 wagons, means we can support up to 127 freight Ethernet train backbone nodes. So these are the active components along the train backbone, which are responsible or have the task to forward the data packets along the train. 2 times 2 contacts in the automatic coupler are needed. And as already mentioned, so we have one variant for this, so this power line plus technology. So to make it short, also here we had some process in deriving which technology to choose. So there was this EDDP project. We started with a list of roughly 15 different technologies. Finally ended up with a short list of 3 technologies. This was single pair Ethernet, Powerline Plus, and a Wi-Fi based solution. But for this project now, which is specifying and also building these demonstrators for the freight trains, we selected as a primary choice a single pair Ethernet. So this here in this picture here we see the typical architecture which we have in one freight wagon, now concentrating on the communication system. So we see on the left and right side we see the automatic couplers. Then we have what we call a junction box. So this is a box purely mechanical, which is interconnecting the different cables and provides a standardized interface to the automatic couplers. Then we have this train backbone nodes, which is called freight Ethernet train backbone node here, which is the communication part, which is responsible first to forward all the data packets along the train, but also takes additional tasks, like for instance to first of all perform what is called this train inauguration, so the establishment of the communication network itself. So if we are coupling vehicles together, then we first need to establish a communication network before we are able to communicate. All this is in the responsibility of this FETBN. And inside the freight wagon, we have what is called a consist network. So this is a local communication network, which is used to interconnect all the components which we have inside a consist. This consist network must not necessarily need to be a single pair Ethernet. So here the idea is more to go in the direction of standard Ethernet and maybe to use dedicated technologies for sensors. For instance, under discussion presently are, for instance, CAN for using this, but also single pair Ethernet could be used for sensors. And last but not least, of course, we have a mobile communication for the connection to the ground side, which is also needed for some of the train functions. Okay, so here, this is just for illustration. This is for the passive car detection wake-up function. I will not go to the details of this circuit diagram here. The basic idea behind is that a DC voltage is applied to the data line, and once those passive wagons are detecting such a DC voltage, they can be woken up. And so this is the first task, and the second task is with this DC voltage, can also be used for passive car detection itself. So if you have some defective cars inside the train which never can be woken up, we need to be able to discover those cars in order to determine the correct train composition, and it's also important for the train integrity finally. And here the idea was to apply some kind of a resistor in each of the cars. And so by measuring then the current, which is driven by this DC voltage, then we are able to determine the number of passive cars for one Ethernet segment. So this is one special function. Next one is about the train inauguration. I already mentioned, so here we would like to apply that what is already available in the TCN standards. On the right we see a process diagram of how those train inaugurations are presently defined in the TCN standard. So there are basically two steps. So this green part is about the train network itself. So first we need to set up the train network if we have coupled wagons together. And in the second step we have to determine the train composition itself. It means that we identify which wagons are connected, what type of wagons are connected, and so on, in order finally to determine the correct sequence of those wagons and also the orientation of all these wagons. So this is the important part of the train inauguration. And as I already said, so we need to have some slight adaptations to the existing train inauguration protocols in order to make them fitting to the freight requirements. About standardization, we already learned a lot about different standards in today's session. Of course, we also need to provide suitable standardization for the freight trains. So, as I already said, so the TCN series need to be adopted. So we see here the different relevant parts of the TCN series. So it's basically affected parts will be the general architecture, so this is the part -1. And then the parts 2-3, which is about the communication profile. So these are the higher communication levels. And the part 2-5 about the Ethernet train backbone. These are the lower communication layers. In our case, this is really the single pair Ethernet. And for those parts, revision has already started, originally for other reasons, but because we are already presently in the maintenance cycle of those parts, it's quite convenient that we also can now do the necessary adaptations to the freight cars. And this is something which is presently an ongoing activity. We still have other parts which are affected, but where it's presently not clear to which extent we need to adapt them. So there are presently no plans, either no plans available or it's still completely open what needs to be done. So this is something which we have to tackle quite soon. I would say latest next year, so we also have to work on the additional parts. So the last slide here, it's about the planned schedule. You see it. So presently we are still in the phase of defining the concepts, defining requirements and the basic architecture of the system. Then in 2024 it's intended to start with first testing activities on a lower level in that case. So basically on prototyping level, and then partly in parallel in 2024-25 it's intended to really start the development of the components which we need for a high TRL level, and also to perform interoperability tests on that basis, because there are different companies involved. All are developing competitive products, and so we have to ensure that the interoperability is finally given. In 2025-2026, Molly has already shown it, it's planned to have these real train demonstrators, where we can also run field tests with this new technology. And if everything works fine as intended, then the deployment can start in 2027 plus. So I think this was my last slide. Yes. So thank you for your attention.